Hello, everybody. My name is Andrzej. I'm a solution architect at Software. You might know us from our technical blog, Scala Times newsletter, Scala conference, and a few other open source activities. But the plan for today is to talk about event sourcing. And I suppose that explaining basics of event sourcing on the second day of a conference about event sourcing is quite pointless. Still, there is no presentation about event sourcing without this classic slide. So let's get it over very quickly. And in classic systems, we are saving our aggregates entities as the most current state to our database. In event sourcing, state in database not exist anymore. I mean, you can save snapshot of a state, usually because of performance reason, but this is totally optional. What you are saving and what is your source of truth are, of course, events. And when you replay events one by one, you will get exactly the same state as on the left side of the slide. But with events, you will also get more business information. So some item was added and then removed from the order, item C. It looks like a pretty interesting business information. Maybe we should send a voucher for this item to this user. Maybe we should send an email with replacement for this item. Maybe this information is completely irrelevant. What is crucial here is that you, as a developer, should not decide what's important, what's not. You should store all business facts and provide necessary data when needed. And fun fact about event sourcing from one of Greg Young's presentations. By the way, Greg Young is one of the event sourcing evangelists. If you don't know this gentleman, well, you should definitely Google him. So the fun fact is that humans have been using event sourcing for thousands of years. The first, let's say, implementation of event sourcing was found in Mesopotamia on clay tablets 9,000 years BC. And it was used for persisting marketplace transactions. So how many ships, bread, grains were bought or sold. And this way, the Mesopotamian trader could very easily recalculate the state of possession. And another famous gentleman, Martin Fowler, in 2005 wrote an article about event sourcing, where you can read something like this. Enterprise applications that use event sourcing are rarer, but I have seen a few applications or parts of the application that use it. And this is kind of sad. 11,000 years in total seems like enough time to validate some concept on production, don't you think? Today we have 2021, and from my observations, which are totally biased, but from my observations, finally this concept is getting more and more popular. Why? Because you are building completely different systems than 15, 20 years ago. And at some level, you simply don't have a choice to move forward, to expand, to scale. You will either implement something that is very close to event sourcing or full event sourcing adaptation. And I'm observing the same patterns, the same problems, the same solutions in basically any event-driven, let's say, system. So why event sourcing? As I mentioned, with event sourcing, you will get complete log of all state changes in the system. This is especially useful for your business. No data is lost, but for you as a developer as well. Why? Debugging. So many times when I was trying to find a bug, it was necessary to replay event by event, and this way analyze what was going on. And trust me, debugging this way is a completely different story. It's a very pleasant experience. It's like Time Machine, but more real. But honestly, from my observations, people invest in event sourcing because of these two reasons. So performance and scalability, and of course, we'll cover this as well later. And last point is, finally, with event sourcing, asynchronous, decoupled, event-driven communications work like a charm. So before we jump into details, let's talk about one more acronym, which is CQRS. So in the command query responsibility segregation, in CQRS systems, the responsibility for handling commands and writes is separated from handling queries and reads. And this separation is not only based on the software level, but also on the hardware level. So different deployments, different hosts, different databases. And you can implement CQRS without event sourcing, but implementing event sourcing without CQRS is quite pointless. I mean, you can, but it will be really, really hard to squeeze maximum potential from event sourcing pattern without CQRS. That's why these two are implemented more or less together. So during my journey with event sourcing systems, I extracted a few different levels of event sourcing implementation. And the first level is so-called transactional event sourcing, where in one big transaction, we are saving all events and all read models. And this is fine. It's really easy to implement. No magic here, zero eventual consistency, but performance of such solution is quite limited. So sooner or later, this huge transaction will become a problem. Still, I'm not saying that you should never ever implement event sourcing this way. Actually, this is a very good entry level, especially if you are working on a startup and you have no idea how many people will use your application, maybe no one, like in one of my cases. Few more links about this topic. I could recommend great articles of my friends how to implement such event sourcing based on SQL database with a lot of examples, and really worth to read it. Also, as a company, we created very small open source project with an example of such implementation. It's in Scala. I'm not sure if Scala is your first language, but let's say you can grab the overall concepts and just copy paste them into your project. So quick summary, easy to implement, easy to reason about, zero eventual consistency, but performance and scalability not so great. Second level. This time, the scope of this problematic transaction is much smaller. We are saving only events in transaction. Very lightweight operation. Any database will love it. Append-only writes is something that most of the databases will handle very effectively. So definitely we improve the command service side. We also introduce another new piece, which is a projector. So something needs to read new events and update read models. This is great because we can launch many projectors. So hooray. Unfortunately, since this level and further, we are entering the eventual consistency world, and we can face two problems. First one, by accident, we can, if we, for example, launch hundreds of projectors, then we can increase the database load, our event store load. Well, this depends on your use case, how many projectors, what is the database, but let's say it's possible. But there is a second problem, which is a lag. So how often should I query my database for new events? So each 3 seconds, each 1 second. I can imagine many systems where an additional second of eventual consistency is simply not acceptable. So what can we do about this? And before, quick summary. So performance and scalability improve, but also eventual consistency, increased event store load with question mark and lags. Third level. Now we are introducing another piece, which is an event bus. And I know that if you have 5 projectors, then introducing event bus most likely will be an overkill. But for some cases, this extra buffer between your event store and your projectors will give you a lot of benefits. What are the benefits? First, we need to query the database only once to check for new events and copy them to the event bus. But the problem of lag still remains. So how can we approach this? We can save events and in the same transaction send them to the event bus. And of course, transaction on 2 heterogeneous systems is a very bad idea. So quick patch for that. We are saving only events in transaction, and then we are sending them in a fire and forget style to the event bus. Of course not. Some guarantees are required here. So at least once delivery, no events can be lost, and events orders must be exactly the same. How to implement this? Well, you could track, for example, sequence numbers. So each event should have its own monotonically increased sequence number. It could be per aggregate. So before you send anything to the event bus, just check if the sequence number is +1, then yeah, you can send it. If it's -0 or -1, then this is a duplicate, you can skip it. If it's +2 or more, then it means that you have a gap and you need to fill this gap directly from the event store. And in 99% of cases, you won't see any gaps, but you need to be ready for some restarts, crashes, etc. Honestly, this is the fastest way to fill event bus with events. Well, there are some other options, but they're database specific. From application perspective, this is the fastest possible way. But implementing this, it's not a piece of cake. It will require some time, a lot of tests, a lot of failover tests, but it's possible. So let's verify our architecture. Query services are stateless services. If you want to scale this part, you just need to launch another instance, put some load balancer on top of it, and that's it. Read model databases, well, you can scale this part because you can have a separate database per read model, separate database per query, not a problem. You can launch hundreds of projectors because you will use some good scalable event bus, and hundreds of projectors for event bus is not a problem because these systems were designed to support such use cases. Scaling event store. This part is tricky. In some cases, it's possible. In some cases, it's quite limited. And it depends on scaling this part. So can we scale command service side? Well, command service side needs to be consistent. And to achieve consistency, you have at least 2 options. First one is locking. But then you need to use a database that support a locking mechanism. So your scaling capabilities here will be limited by your scaling capabilities here. Another approach, if you need to handle huge load, is to implement a single writer principle. But then to scale this part, you will need a clustered sharded solution. And here is our final version of Uber turbo scaling event sourcing architecture. Please don't start with something like that. The goal was to show you all possibilities, and now your job is to pick the level that suits your needs. Most likely, you don't need so complex system, especially as the first iteration. Yeah, so summary, performance and scalability, really great, but eventual consistency, complex implementation, I will not lie to you. And if you want to read more about this locking versus single writer, then just follow the link. To cover this topic fully, I should mention about two alternatives. First one is CDC, so change capture data. This is a very nice way to copy events from your event store to the event bus, or even to replace event bus. But it's possible only for a single host databases. For distributed databases, managing CDC, it's a nightmare. So don't go this path. And because we desire so much streaming capabilities from our event store, maybe we could use event bus as an event store. And here is a link to my CTO article about how to implement event sourcing based on Kafka. Really great article, and I hope that I'm not signing my contract termination right now. Be careful with that. I mean, this will work awesome for some use cases, but not as a general purpose solution. So make sure that you understand all Kafka concepts correctly and you know the limitation of this solution. Not covered today, but worth to check. Command sourcing and events collaboration, very interesting topics, but let's say it's your homework. So we know what we want to implement, or at least the holy grail architecture. Now, how to implement this? And we can go with custom implementation, library, or framework. And if you look at event sourcing from a domain perspective, this is quite trivial architecture. So we have three main building blocks: commands, events, state. And we just need to implement two methods on state. So first one is process command and return list of events, and then apply the second method, apply event and return new version of the state. So that's why many people think that, yeah, you should implement event sourcing from the beginning by yourself. This is partially true. The domain part, yeah, for sure, you can implement this by yourself, and you should. But your application will be production ready when you also deliver few more set but require features like snapshotting, failover, recover, debugging, sharding, serialization and schema evolution, huge topic, concurrence access, etc. And trust me, implementing this from the scratch by yourself is a recipe for failure. So for that, I would recommend to use some existing solutions created and tested by many programmers. Unfortunately, using any framework has its hidden cost. Here is an example of classic JPA implementation. So you have a business entity with some business code and JPA annotation. It looks okay, right? No. What's wrong with this code? You just mix two really important responsibilities. First one is our domain code, obviously. And second one is some infrastructure instruction, how to persist this entity. And someone could argue, so what? If I remove all this annotation, the code will be exactly the same. True. But this is very simple example. And trust me, all tutorials are based on simple examples. And then you need to implement something more real. Let's say that I would like to have map of maps in my domain model. I suppose that translating such field to a JPA will be problematic. I'm not sure if it's even possible. Maybe it is. Most likely, I will use something more JPA compatible. And personally, I hate such compromises where my persistence layer is dictating me how should I implement my business code. Unfortunately, the same story applies to event sourcing frameworks. So here's an example from Axon framework. Domain aggregate mixed with framework annotations. The same story with Lagon framework. So user entity extends persistent entity. If you check out the imports, you can see that there is some JSON formats. Wow, on my domain level, I don't care about JSON. I don't care about serialization. I just want to write my business code. That's it. So how to deal with it? Back to the basics and proper packaging. You can start with something like this. And don't get me wrong, this is not like a free tier or something like that, this is completely different. In your business module, you could create a domain package and put all the event sourcing related pieces to this package, so state, command, events. And application package is a place for a framework. If you want to check out the full source code example and read more about this, just follow the link. The article is pretty old, but the overall idea is still valid. And thanks to such approach, your event sourcing user aggregate will look like the snippet on the slide. So first of all, no imports to any frameworks, just two crucial methods. And I'm not saying that you should implement all your business code in just two methods. Those are only entry points to your domain aggregate, nothing more. And this code will be trivial to write, to understand, or not. It will be exactly as complex as your domain. What is trivial here is how you will test this code. You don't need actor system to test this code. You don't need to launch Spring context to test this code. You will write simple unit test. That's it. And for me, this is a really huge advantage. To test my domain, even with 100% coverage with simple unit tests. So once again, application package for all the set stuff, and domain package for domain logic, domain validation, and zero event sourcing framework imports. So if at some point I will decide that, okay, this event sourcing solution is not good for me, then I would simply delete application package and my domain will be untouched. Most likely this will never happen, but still it's good to have a separation of concerns in your code base. This way, it will be much pleasant to add new features and extend the code base, trust me. So I'm using very often a Notion library versus framework. What's the difference? And usually removing a library from your code base is much simpler than removing a framework. And a good example could be Akka Persistent versus Lagom. Lagom is a full-blown event sourcing framework based on Akka Persistence, by the way. And everything is well organized. You just need to put command here, events there, and Lagom will do the magic for you. And this is great, unless you have a very specific business use case, and then you need to adjust it to be Lagom friendly. On the other hand, Akka Persistence is one level of abstraction lower. It will give you all the technical functionalities to build a production-ready event sourcing solution, but you will need to handle more stuff by yourself. Also, you will get more freedom. Which choice is better? It depends. But I suppose this is a story for a whole new presentation. And I'm not saying that you should never, ever use a framework. No. Just take your time, validate existing solution, create some proof of concepts, understand the limits of this solution, and then go with your choice. From my perspective, when it comes to Akka Stack, I could honestly recommend Akka Persistent Typed, still not a framework, but this time it's much harder to do something stupid than in Akka Persistence classic version, let's say. So I could honestly recommend it. So let's say we know what we want to implement, how, now where to store events. And options are like file, relational database, event store, MongoDB, Kafka, Cassandra, and probably many others. This time, the storage selection depends on the previous choice. So if I go with custom implementation, then yeah, I can use any database I want. If I will choose Akka Persistence, then my choice is limited to relational database and Cassandra. That's of course not true. You can use Akka Persistent with DynamoDB, Google Spanner, and many, maybe not many, but few other databases. But for sake of this presentation, let's say that you have a choice between relational database and distributed database. And the relational database seems like a safe option because everyone knows how to use it, how to set it up, how to maintain it on production even. So it's a safe choice, right? It depends. It depends on your load. So relational databases were designed to work well on a single host machine, and vertically scaling a single host machine can be a problem sooner than later. That's why I would recommend to use, or at least to analyze, distributed databases like Cassandra. Why? Because you will get partitioning by design. Your data will be spread across all nodes in the cluster. You will get replication by design. So in case of some node failure, you always can read your data from a different node. Leaderless architecture, in comparison to Mongo, where you have classic leader-follower architecture, and in case of leader failure, bad things could happen. Here, any node can handle any query, so no single point of failure. Cassandra is optimized for writes, especially important for event sourcing. So just 2 nodes can handle 100,000 transactions per second. And of course, this is some marketing materials, but let's say if this is not enough for you, you can always add a node and scale it horizontally, almost in a linear fashion. Beware that there's growing alternative to Cassandra, which is ScyllaDB. Basically, ScyllaDB is Cassandra without JVM. The same concepts, the same protocols, but this time C++ and C*lib, and even bigger throughput. At some point in time, it was not fully supported by akka persistence. I'm not sure what is the status right now, but yeah, for sure, it's worth to know that there is something else. Okay, so we know where we want to store events, now how to store them. And options like plain text serialization, JSON, XML, YAML, and binary formats. And I know that most of you will choose JSON anyway, but let me show you some alternatives. First, let's start with comparison plain text serialization and binary serialization. So plain text, yeah, it's human readable. It's very convenient to just select your events from database and analyze directly from the query results. In case of binary serialization, you need to add additional step and transform bytes to something human readable. Is it a problem? Well, if you need to debug something on production, you will very quickly create a tool that will do this automatically for you. Of course, with binary serialization, such tools should be created up front, but there is nothing like a good motivation from production, and burning production is like best motivator ever. With JSON, you can face very strange precisions with issues, with number precisions, and just follow the links from the table. Binary formats are more compressed. The actual saving depends on your events model. In my case, it was from 60 to 70% of saving on a disk space. And yeah, someone could argue that well, storage prices are cheap, so is it so important? Well, yeah, storage prices usually go down, but at the same time, the amount of data we are gathering is growing even faster. Not to mention about replication required by some databases. So I think this point is quite important. All benchmarks are pretty consistent. Binary serialization is much faster than plain text serialization, which shouldn't be a surprise because in case of plain text serialization, you need to add a lot of additional steps to serialize and deserialize something. And last point, really important, full schema evolution support. With good schema evolution support, you will be able to versioning your events without typical versioning pain. So no more _v1, _v2. And in case of binary formats, schema evolution support is on a completely different level than in case of plain text serialization. So clearly, binary serialization is a pretty nice option. Now, which one should we choose? Java serialization is slow, it's dangerous, it's out. Cryo, very nice, very fast, but it will work only on JVM applications. So let's not limit our architecture only to JVM applications. Thrift from Facebook. When it comes to functionalities, it's almost the same as protocol buffers, but I know the second better. Also, I think that the documentation and tooling is way better in case protocol buffers. So we have Avro from Hadoop and protocol buffers from Google. Which one is better? And now I could spend another 40 or 50 minutes just explaining the difference between two of them. But we will do this very quickly and we'll jump directly to the conclusion. So both will support many languages, although the actual support might be different. So let's say Avro support in Python is, you can use only generic schema approach. So you will not use full potential of Avro. Protocol buffers support in Scala is way better than in Java, which is a surprise. Usually it's the other way. Yeah. So speed, both will be very fast when it comes to serialization and deserialization. Both will produce really small payload size. Both will give you full compatibility support. So backward compatibility is quite obvious. You need to be able to read old events from your database. But forward compatibility is also very useful if you are planning to have rolling updates and you would like to, for example, add a new event and without the need to update all projectors at the same time. With forward compatibility is possible. So in both cases, you can add a field, remove a field, even rename a field. I suppose that in case of protocol buffers, it's easier, but it's possible in both cases. So a tie again. So what's the difference? And the difference is, wait a second, the difference is in schema management and the overall impact on the domain. So in Avro, especially in Scala, you will write less boilerplate code because you will generate your Avro schema based on existing case classes. Of course, this might pollute. If you start using some Avro-specific constructions, this might pollute your domain. Also, reader and writer schema distribution in Avro is quite painful sometimes. So schema registry is not always the best solution for that. In case of protocol buffers, schema is first. So based on that schema, you need to generate some classes. So you will create a lot of boilerplate code and a lot of methods like from something serializable to domain, from my nice pretty domain to something serializable. But this way, your domain will be perfectly separated from your serialization mechanism. Now, which choice is better? It depends. If you want to check out the full comparison, just follow the link to my article about that, and you will get all the information from the slides I just skipped. Okay, so we know how to store events. Now, what to put to the event payload itself? And most people will start with a delta change. So let's say that I would like to emit user funds withdrawn, and I will put only the amount of the withdrawal. And this is nice, it will work. But from the projector perspective, this is quite painful to process such events. Because let's say that I would like to write a projection that will send an email if a user balance is below some threshold. So it will be nice to add and enrich this event with a current user balance. This way your projection don't have to calculate anything or ask external resources and worry about time. It will be really simple to write. The extreme version of events enrichment is to put the whole state to the event. I've done this once, and I think in that particular case, it wasn't such a bad idea. Although the cost of such operation is that is of course payload side and pretty complex schema to support in future. Also, beside the business information, most likely we will add some technical information like sequence number, I already mentioned, creation timestamp, event ID, command ID that was the source of this event, correlation ID if you want to track the whole business process. So at this point, I think we know everything. We know what we want to implement, how, where to store events, how to store them, how to design an event. So let's implement some event sourcing. Where? Everywhere. No, this is the first major problem with event sourcing adaptation. As you might notice, this pattern is very powerful, but also very costly. So in your core domain, you should choose even some subset of this core domain. And maybe this is the place for event sourcing, maybe not. So remember about this slide, and now we could move to more general problems. And the first one you might think of is the time required to replay all events. Surprisingly, this is a very fast operation to load, let's say, 100 events and recreate the state, even 1,000 events. Still, many people ask about this, so we can start with this one. So the solution is, the first solution is snapshotting. So make sure that your event sourcing framework, event sourcing solution supports snapshotting. Snapshotting is basically saving your state to a database every X events. And then if you need to recreate the state, you need to load the latest snapshot and events after this snapshot. And before you enable snapshotting, make sure that you really need it, because the hidden cost of snapshotting is that you will need to manage the state schema. Another approach would be to load everything in memory and keep it there. So once you recreate the state, it will wait to handle next command. And that's why event sourcing based on actor model is so fast, because everything is memory. It's really, if you don't have to create a database, it's hard to implement it faster. This technique is called write through cache, and if you want to read more, please follow the link. Yeah, because everything is memory, you could expect out-of-memory exceptions, but out-of-memory exceptions is not something new in Java and in different languages, so make sure that you are not doing anything crazy with your state. Learn some memory analyzer tools and you should be fine. And many people also ask, should my state be immutable or not? By default, of course, immutable. It will be much harder to create out-of-memory exceptions. It will be much easier to manage the state in multi-thread environment. But as always, it depends. So in my case, when we are using immutable list, we are able to process 17 operations per second. When we switch to good old-fashioned Java tree map, 2200 operations per second, and this difference is so huge that it cannot be simply ignored. So we go with mutable state. Still, we are using actors, so my state is protected by the actor. Yeah, so I'm pretty comfortable with that choice. And before you switch to mutable state, make sure that you run some benchmarks and you have some data to support such a decision, because you could be surprised by the actual results. Okay, fixing the state is quite boring. Updating. Okay, handling duplicates. This is a nightmare in the distributed system. Let me tell you a story. This is a fairyland, and this first unicorn is called exactly once delivery, and the second one is called transaction between two aggregates. None of them exists. You know, I'm a happy father of twins. So when I'm saying that there is no such thing as exactly one delivery in a distributed system, trust me, I know what I'm talking about. So yeah, if someone is telling you that you can achieve exactly once delivery in a distributed system, if you use this or that, either this person is lying to you or not telling the whole truth, which is basically the same. Why duplicates? First, we can produce them on our producer side. Even if you are able to filter out duplicates here, your projectors should be ready to handle them anyway, because they can arrive in case of some restarts, crashes, etc. So the best way to handle this situation is to have idempotent updates. And well, processing the same event twice will not change anything. This is super. But some projections are not idempotent by definition. So let's say that you aggregate something and counting average or whatever. So in this case, processing the same event will corrupt the result. And in this case, you could use once again sequence numbers. So store your read model together with the sequence number, and then if you use the same sequence number, this transaction will fail. Also, you can check if the sequence number you are processing is +1. If it's +1, then yeah, you can process it. If it's -0 or -1, this is a duplicate, you can skip it. So that's the solution. And this brings us to the next problem, broken read model. So when you can break your read model? Two reasons for that. Software reason, so a bug in the code, and hardware reason. So some read models are more fragile than other ones. And Redis is a very good example. In case of Redis, you can always lose some data. And frankly speaking, quite a lot of them, depending on your configuration. So in this case, you can always delete the whole read model and rebuild it from the beginning. This is awesome feature of event sourcing. I use it many times. It gives you a lot of flexibility and a lot of comfort, but sometimes, in case of hardware failures, especially, you don't want to process billions of events from the beginning. You just want to fix the read model. So in this case, you can store read model updates together with the currently processed offset from your, let's say, event bus, from your event stream. And in case of some failures, you just need to read the latest successfully saved offset and start processing from that offset. So that's the recipe for a broken read model. Multi-aggregate transactional update, the second unicorn. So if you need to update in transaction two aggregates, just stop. This is a red light, time for pause. Start with rethinking your aggregates boundaries. Maybe you have two thin aggregates, and if you simply join them, you will eliminate this problem very easily. Sometimes your aggregates boundaries are fine and you still need to handle it. In this case, the only way to do this right is to apply compensating action. And compensating action could be optimistic or pessimistic depending from your business perspective. It's not like official names. I just made it up to explain it. So let's say that we are building a very simple application for selling tickets to cinema shows, and we have two aggregates. First one is a user, which represents a user with some funds, and we can charge the user. And second one is a cinema show where you can book the seat, and you cannot sell more seats than the available number. So in pessimistic compensating action version, pessimistic from the user perspective, first we will charge the user, then we will book the seat. And that was the last seat. Unfortunately, our application are used by many users concurrently. So right after charging the first user, someone else could book the last seat. So in this case, booking for the first user will fail. And it will be nice to have a transaction here. Forget about it. Look at it as a transaction between two microservices. And as I mentioned, the only way to do this right is to apply compensating action, so simply refund the money. From optimistic perspective, first we will book the seat, then we will charge the user. So in case of concurrent booking, we will enter the overbooked state. And now the question is, should we charge the user? And it depends. I suppose in case of cinema business, it's not a good idea. But in case of planes, well, overbooking is a part of a business strategy. It's perfectly fine. And I noticed this many times that maybe not in cinema, but in theaters, especially if some show is very popular, then they can always add extra chair and overbooking is not a problem. So different business use cases, different strategies. One thing is missing in the story, how to implement this. And for that, most likely you will need Saga. And Saga could be implemented as a choreography. Basically, in this case, you are reading 2 or more stream of events and verifying some inconsistencies. Or you can implement Saga as orchestration. So there is one coordinator with the whole business process. And the first one, I mean, choreography is way easier to implement and to start. Orchestration is much harder to create, but it will give you a single place with probably well-documented place with the whole business flow. Implementing Saga is not a piece of cake, really, because Saga should be persistible, so it must survive restarts, crashes, etc. You cannot assume any order of events. So it should be relevant for the implementation. There will be always some time window limitation. Let's say that I just consumed booked event. Now I'm waiting for charge event for 10 minutes and I didn't see this event, so I need to apply compensating action. But this event will arrive to me after 12 minutes. That's why compensating action must be commutative. So a lot of consideration. A few more links about sagas and piece of advice from my side, try to avoid them. Sometimes it's possible. So in case of some frameworks, having larger aggregates, it's not a problem. In some cases, unfortunately, it's a problem. And in some cases, you still need to handle sagas. So be ready for them. Event sourcing and Rodo. I'm not a specialist here, but let's say your application should give a user right to forget. And how to do this when you cannot delete an events actually. The technique is called data shredding. So basically you are encoding all the sensitive business information. So your states, your events, your state, views, your read models, etc. It seems easy, but managing those encoding keys, it's not a piece of cake. Also, you need to remember about retention policy of your message brokers, backups, logs, and you need to migrate data before Rodo. So piece of advice from my side, don't use event sourcing for sensitive user information. Simple as that. Sometimes it's possible. Okay, I think that's the last topic. In our final version of our architecture, we are using a cluster solution. And when you are using a cluster, you should be ready for a nasty problem, which is split brain. What is a split brain? So let's say that we have a cluster with 5 nodes and some load balancer on top of it. And load balancer is a dummy machine. It will just route all your requests to all nodes in round-robin fashion. So let's say the first request to update user 1 will go to node 5, but this node is in the cluster, in a sharded cluster. So this node knows that actually the node responsible for updating this user, because this is distributed single writer, is node 1. So it will redirect this command, this request to node 1, and node 1 will handle it. And then we have a disaster in our DC, a broken switch or something like that. So the node 1 and 2 cannot communicate with 3, 4, and 5. But from the load balancer perspective, nothing changed. All nodes are working fine, except that they just create 2 smaller clusters. And in this case, request to update user 1 from node 5 will be redirected to node 4, because in the smaller cluster, node 4 is now responsible for user 1, but next request to update user 1 will go to node 1, and in this smaller cluster, node 1 is responsible for user 1, and then there you go. Classic split brain scenario. You just lost your single writer principle, and fixing the state after this failure is a nightmare, really. Sometimes it's not even possible, so some data could be lost. So in case of clusters, some best practices, remember about the split brain. In case of Akka cluster, you need to enable Akka split brain resolver and configure it correctly. Also, you should enable very good monitoring and alerting, not only your cluster, but let's say your all machines, but especially your cluster. You need to know what is going on 24/7 with your nodes. create a lot of failover tests, try to break the cluster however you want, create your own chaos monkey. Cluster should be also deployed on dev and staging environment, not only on production, just to test it better, and keep it as small as possible when it comes to code base and number of nodes. So managing a cluster with 5 nodes is much easier than managing a cluster with 15 nodes. So if some functionality can be moved to a stateless service, just move it to the stateless service, because scaling a stateless service is a much easier task. Summary of this whole presentation. Event sourcing is great, it's awesome, you will love it the second time you use it. The first time will be painful. And to be less painful, carefully choose your event sourcing library framework. Really, take your time, do it slowly. There is no perfect database for event sourcing. Sorry, only reasonable compromise. Understand event command, event state, schema evolution. Really, this is extremely important topic. I know it sounds boring, but really, take your time. And I'm not talking about hours, I'm talking about days or even weeks. Really important stuff. Eventual consistency is your friend. Do not fight with it, just learn how to deal with it. Scaling is complex, no magic here. So if you launch Cassandra cluster, Kafka cluster, Akka cluster, well, it will require a lot of work. But once you do this, the reward will be proportional to the effort. And whole event sourcing is like turning your database inside out. Finally, the asynchronous communication between microservice is way better with event sourcing than without. Unfortunately, we didn't have time to cover this topic. And the last point, a little bit philosophical. So once you create your first application, where the core of this application is basically to create the stream of events and then process the stream of events, you will realize that all big players are using the same techniques. So Netflix, Facebook, Twitter, whatever, they are all using the same techniques. And because this is the recipe for building reactive, scalable, elastic, really awesome application. Definitely worth to learn it, definitely worth to expand your toolbox with that. It will change your mindset in a good way. If you want to learn more, but you don't have time for that, some time ago we launched a few online on-site workshops where we can teach about how to start with actors, how to build reactive event sourcing solution, then how to scale them with a cluster, and how to test them, how to test the performance of these solutions. And that was it. Thank you very much for your attention. If you have any questions whatsoever, I'm here for you.